In this unit, we discussed hypothesis testing for a single population. What we mean by single population is we want to know how a population parameter from one population relates to a particular hypothesized value. The null hypothesis is the statement that we assume to be true unless evidence from a sample compels us to conclude otherwise, where otherwise is represented in the alternative hypothesis. The alternative hypothesis is contradictory to the null. For example, if we're addressing a hypothesis about a population mean, the null hypothesis, H0, might be that the mean of that population is equal to mu0. The alternative hypothesis, H1, would be that the population mean is not equal to mu0. We can answer hypotheses about equality versus strict inequality, or we could address greater than or equal to versus less than, or we could address less than or equal to versus greater than. Note that those three pairs are the only three options that we can have. A statement that deals with equality must be in the null hypothesis, and the alternative hypothesis must be contradictory. So those three options are the only three that we have. And any statistical statement about a parameter of a single population will fit into any of those three options. If you want to test if a population proportion is greater than 0.7, then we look at those three options for a greater than statement. That's in the alternative hypothesis of this set. If we want to know if the variance of a population is equal to 14, we have to look for an equal to statement. We get a strict equal to statement with this set of hypotheses. The population parameters that we can formulate hypotheses for are means, proportions, and variances. And the way we draw conclusions about a hypothesis is by using a test statistic. The test statistic compares the evidence we've collected, that is, the sample statistic, to the hypothesized value. If the sample evidence is significantly different from the hypothesized value, if the difference between the sample statistic and the hypothesized value is big enough, then we reject the null. And we account for variability in sample size with all of our test statistics, and we use a measure of confidence to draw a conclusion about that test statistic. We have two approaches for drawing such conclusions. The first that we discussed is the critical value approach, where we compare the test statistic to a value on the axis of the appropriate distribution called a critical value. The critical value gives us the level of evidence beyond which the rejection region lies. The rejection region has area alpha, so the critical value is a function of alpha. That is, we have to pre-specify a level of alpha and find the corresponding critical value with which to compare the test statistic. If the test statistic lies in the rejection region, we reject the null. If it lies in the non-rejection region, we don't reject the null. The second approach that we discussed is the p-value approach. Here we find the area in the tail, or tails, associated with the test statistic, and that is the p-value. We compare the p-value directly to some value of alpha. If the p-value is smaller than alpha, we reject the null. If the p-value is greater than alpha, we do not reject the null hypothesis. With the critical value approach, we compare the test statistic to the critical value. This comparison is made on the z, t, or chi-square axis. With the p-value approach, we compare the p-value to a significance level, alpha. This comparison is made with the areas under the curve. Note the difference between the two approaches, though they give us the same answer. The p-value is the more commonly implemented approach, as anyone can look at a result and draw a conclusion with their own level of alpha. For example, someone may interpret a p-value of 0.09 differently than someone else. If someone wants to be particularly convinced of the result, a p-value of 0.09 may not be convincing enough to reject the null. For someone else, it may be sufficient. The p-value approach is implemented in software packages. If you continue on with the study of statistics, say for analytics applications, you'll work with more sophisticated statistical analyses in software packages, and those packages will return a p-value. Also, p-values are provided in scholarly work in journals. The authors will draw a conclusion, and the reader can agree or disagree with the author based on the p-value. So that concludes the unit on hypothesis testing for a single population. In this unit, we have a hypothesized value for a single population, and in the next unit, we'll extend this idea to compare two populations against each other.